One of the important properties of fluids are to consider instabilities, which is where when you perturb the medium, unlike a sound wave where the perturbation happens and it decays with time, an instability is a situation where a perturbation comes about for whatever reason and it grows with time. And these can have very important effects in mixing of gases inside stars, inside the interstellar medium. They can have the important effects in determining collapse inside molecular clouds. And so they're key to get our handle on as part of our study of fluids. And so over the next several lectures, we're going to be developing up several different types of instability processes and what initial conditions set those about. But the first one that I want to use is to talk about the convective instability, because it's something that's a little bit easier to understand in an initial sense. And we can build up the formalism for developing an instability for the convective instability. And then we can take that idea forward as we talk about Kelvin-Helmholtz instabilities, Rayleigh-Taylor instabilities, and some other ones that I'd like you to be able to recognize as part of your fluids understanding. So let's start off with talking about the convective instability. So the convective instability is one that happens where we have a temperature change and in the presence of a gravitational change, or a gravitational field, I should say. But let's just think about instabilities generally. So if we think about instabilities generally, we start with the idea that we have a steady state scenario. So that means that the partial derivatives with respect to time are equal to 0. And if there's a small perturbation that grows with time, then you would describe it as an unstable medium, which means that it's very difficult to go backwards and figure out what the medium was like before this perturbation. So the perturbation continues to get bigger and we can't recreate the initial conditions. The alternative approach is that you have a small perturbation that decays with time. And that's stable. And an example there is a sound wave, where the decays with time, but we can recreate the initial conditions based off of our understanding of wave equations. So let's start with the convective instability. And we're going to consider a system that changes adiabatically. And we're going to draw a couple of pretty pictures of our scenario. So what we want to consider is that we have two regions, and we have we're going to lift one region, the lower region, up to the higher height. And we have a gravitational field. In these initial regions, we have density rho and pressure P. And outside of it, it's rho and pressure P. So this is in the equilibrium sense, and it's constant. We just take a packet, we just enclose a packet. Now we're going to lift that packet up against gravity. And when it gets to its higher position, it has a density rho star and a pressure P prime. And the medium surrounding it has a density rho prime P prime. So what happens is that the pressure equalizes very quickly as we move this packet up. The heat takes a bit longer to transfer through, and so we have a density that is no longer in equilibrium. Okay, so if rho star is less than rho prime, then the perturbed element is buoyant, and therefore the system is unstable. Alternatively, if rho star is greater than rho prime, then because this is in the presence of a gravitational field, what happens is that that element just sinks back and the system is stable. It just comes back down to where it was and everything's okay again. So the perturbed element sinks back and it's stable. Okay, so that's the scenario. That's the picture that I want you to imagine with rho and P, fluid element lifted above new density, new pressure, and different than what is in the surrounding medium because this has some gradient in our pressure there. So let's consider how these equations work out to see what system would produce this unstable versus this unstable system. So let's first off assume that we have a simple equation of state where the pressure is given by the density to the gamma power, and that means that pressure prime is equal to rho star prime, and we can combine these two equations to say that the perturbed density is equal to the initial density times the ratio of the pressures. It should be a P, ratio of the pressures, the pressure at the perturbed position over the initial pressure to the 1 over gamma power. So where can we go from there? Okay, well, the perturbed pressure is equal to the initial pressure plus the pressure gradient times the displacement in distance z, where I've let z be against my gravitational field. And likewise, rho star is equal to rho plus, this follows from, that should be rho, sorry, rho over gamma p, pressure gradient times my displacement. So this is the density of the displaced item, displaced element. And we want to see how does that compare with the density external to the medium in order to know whether it should be stable or unstable. Because remember, as I said before, that the system would be unstable if that new density, rho star, was less than rho prime, which is the density at the position of its new position. So we'll work from there and combine these equations. So let's say rho prime, what is the density of the medium outside of this element, is equal to rho plus d rho dz times the displacement. And if we let P equal K rho T on mu mp, which is just a standard ideal gas law, then we find that rho prime is equal to rho plus rho on p dp dz minus rho on t dt dz, where I've just taken the derivatives of the two different terms, which will have gradients, times the displacement. So how do the two terms relate to each other? How does rho star relate to rho prime? Because if rho star is less than rho prime, then it's unstable. Well, we can take the equations that we've already derived for those two terms, rho star and rho prime, which I've just derived in the previous slide, and take the difference of those two, and we have 1 minus 1 over gamma rho over p dp dz plus rho over t dt dz times the disturbance distance, so the displacement distance. By definition, dp dz and dt dz in my scenario that I've set up are negative. So the medium is stable, which comes about if rho star is greater than rho prime. It's stable if dt dz is greater than 1 minus 1 over gamma t over p dp dz. Oops, should close that parenthesis. So we can see that if dt dz is greater than 0, it's stable. And this is the convective instability is usually written in the form that the absolute value of the temperature gradient, this is the stability criterion. So it is stable if the absolute value of the temperature gradient is less than 1 minus 1 over gamma t over rho dp dz. And that's the stability criterion. This is most often used in, for example, accretion disks, where it's also called the Schwarzschild criterion, and it defines whether the accretion disk is stable to convective instability or not based off of the temperature gradient of that particular system. Now we'll stop sharing there. I'll stop on talking about the convective instability. It's not one that we're going to put into play a lot, but it is one that is important to develop just the idea of how an instability works and how it continues to grow. We're going to move on in our next lectures into the Kelvin-Helmholtz and the Rayleigh-Taylor instabilities, which are very commonly observed in a number of different situations and are some of my favorite instabilities to play with.